Hey everyone. So, in this example, in chapter 28 on magnetic fields, we have a rigid conducting rod with loops at the ends that are around two vertical conducting rods such that the connection points are allowed to freely move, right? And that allows this horizontal rod to either move up or down while still remaining in contact at both of those joints, we'll say. Okay, and because of that, this loop here that's connected to a battery, right, that's able to provide a current of 5 amps that's running counterclockwise around it. Okay, so that's a steady current of 5 amps. That horizontal rod is of some length, right, 15 centimeters, and it's in the presence of a magnetic field, which we'll call B. And our job is to determine if it's into or out of the screen. Okay? And by the way, the circle with the X means into the page, and the circle with a dot in the center means out of the page. Okay, just so you know. And so if this rod is free to move or free to slide, well, what forces are it or is it subjected to? Well, quick free body diagram. Okay, that was easy. There's always gravity, and we know there's a gravitational force because it has some mass, right? It's made of some non-zero stuff. So force of gravity down, and that's counteracted because of the third law by another force, and in this chapter, that's the magnetic force, FB. And so this might harken back to chapter 5 and Newton's laws, and you'd be right. Okay? It doesn't say anything about friction, but technically there would be in between the contact points, right? But we're ignoring that for right now. So let's write out a second law equation, right, in the y direction for this rod that's sliding down under the influence of gravity. We ultimately want to find the value of the magnetic field and which way it's going, into or out of the page. So when we do a second law analysis, we have to choose a positive direction. So let's say plus y is up. If you chose plus y is down, that would be completely fine too. You'd get the same answer. Okay, but I'm just doing up. So that means we have FB vector plus FG vector, and that equals our net force of MA vector. Okay, just very generally. The magnetic force, I'm not going to write the equation again yet. The magnetic force is of the form the charge times V cross B, right? And so that's the magnitude of the charges that are moving. In this case, we're to assume it's an electron, right? A valence electron. That V, right, this V here is not the speed that it's falling down, right? That's the speed for the particles or the charged particles moving in the wire as part of that current. That's what that V is. The magnetic field is the magnitude of the background field. That's what we're ultimately trying to find. And so if this is a cross product, we need to know the angle, right? Or it would be helpful to know the angle in between. Turns out we do, right? The velocity vector for those particles is in the same direction as the current, right? Kind of by definition. So the velocity is to the left. The magnetic field tells us, or rather the problem tells us, that the magnetic field is perpendicular to the screen. So that means that V is perpendicular to into the page or out of the page. And so the angle is 90. And so when evaluating the magnitude of this cross product, QVB times sine of the angle between V and B, that's 90. Now let's write down the magnitude of gravity. Well, that's easy. mg, the direction is downwards, so we have a negative, or rather I should say The negative is because G is going the opposite direction of our positive direction. That's why it's negative. Not necessarily because it's going down. Okay? And the acceleration is 0 because the problem tells us it's moving at a constant speed. Okay? So that's our magnitude equation. Okay? So ultimately QVB equals mg. However, there's a problem now. We don't know the speed of the charges in the current, right, across this wire. We don't know the magnitude of V. So we can't necessarily use this form, QV, right, QV cross B. We can't use that form. It turns out that, thankfully, there's another form, right? I might have enough room here. QV cross B. Let's see the alternative form for the magnetic force. Well, if you think about each particle, right, in that conducting wire, it's moving just a little bit, right? Just an incremental and infinitesimal amount. Let's multiply this expression by 1 and see what happens. And by 1, I mean by dt over dt, right? If we're multiplying by 1, we can make the numerator and denominator whatever we want as long as they're the same. So let's see how this changes things. We have, I'm going to do this. I'm going to, in blue here, let's see this. We have, I should write actually, and I don't have enough room. Sorry. Let me back this up a little bit. FB equals D, right? Let's take this as a differential now. For every particle moving along this wire here, there's a differential or an infinitesimal amount of force on a differential or infinitesimal amount of charge. And so now we can do what I was going to do and take dq divided by dt. What's that? That is a current. I'll write it as capital I, or some books have it as a lowercase I. I guess I should keep it lowercase like I used last chapter. That's current. And then in red, let's do another color. In red, what is V dt? What is V times dt? V times dt? Well, that is just the differential distance. We'll call L, right? The differential distance or differential length that those particles move, right, under that differential force. So thus, evaluating that, we have it as such. Okay, so let me write this with those steps in between there. So now we have dq over dt times v dt, and that's crossed with b. That gives us a current times our dl cross b. It's still a cross product. We just multiplied by 1 and looked at what we got, right? So now it's in terms of the current and the distance, and that's what we have. So if you want to write this actually back with the full force, you don't need that differential anymore. It's just L. Okay? Now let's plug that into our second law equation. We have the current, we have L, B, the angle in between is still the same, so it's still sine 90, which is 1, minus mg, which is 0. And now it's straightforward to solve for B. And so the mass is 0.015, plugging in all of the numbers given. Little g, 9.81, divided by the current magnitude of 5 amps, and the length, right, the total distance from joint to joint, 0.15, and we should get looking at my notes, 0.196 Teslas. And that's our answer. And our direction for the magnetic field, well, if the velocity was to the left, or in other words, in our amended equation, the length was to the left, we'll call that L, and such that we have a force upwards, right? If you put your pointer finger in the direction of L, the first vector, your middle finger in the direction of B, the second vector, such that your thumb is in the direction of the third vector, or the resultant, F, that means that B has to be out of the page. Okay, so pointer finger, middle finger towards you, such that your thumb points perpendicular to both of those and is upwards, thus counteracting the pull of gravity.